Again, we use this one. F forward rate is basically this one, L and Z or T, 0T over here, like this one. So this one, and then because we know A, so we can calculate, we can take derivative A with respect to T. If we do A with respect to T, A looks like this one, so we can calculate A with respect to T, right, over here because it's T, right? So we can calculate this one, right? And then if we take derivative again, we can recover theta. So theta T is partial F partial T plus gamma star F and sigma of this one. Here, this is from data, right? This is from forward rate data. We know this one. And this is from historical data. As I explained, this gamma star is from historical data. It is speed of mean reversion. How fast interest rate convert to long-term level, speed of convergence. And this is again from data, and this is again speed of convergence, and this data. So from this one, we can find the theta t, and once we have theta t in this way, then we have everything consistent. Model theoretical forward price is exactly same to observed theoretical forward price. Therefore, theoretical bond price is exactly same to observed bond price, and everything is consistent to each other. So we can calibrate theta. Once we calibrate theta, then we can go back to original Hyoung-Goo model. So this is original Hyoung-Goo model. So using forward rate data, now we calibrate this one. So we can completely characterize the Hall-White model. Once we completely characterize the Hall-White model, then we can find the derivative price that is depending on interest rate. First, again, same. dz, again, dz is same distribution, epsilon root dt. And again, epsilon is standard normal distribution. So first, we select a random number. We generate random number from this standard normal distribution and multiply. Let me change the color. So what we do is first we simulate standard normal distribution. From this standard normal distribution, we set a random number, then we multiply root dt, then it generates dz. Once we generate dz, then we multiply sigma, which is from historical data, and then we add dt, rt, which is today's. We start from today's interest rate, and then we multiply this one, and we again add this calibration term. Then we can simulate change of interest rate. By iterating this process, we can simulate the future interest rate process or future interest rate. For each future interest rate, in other words, from this simulation process, we can simulate future interest rate. And for each simulated future interest rate, we can simulate a future derivative price. And we can do this like million times. We have million number of future interest rate. And for each interest rate, we have like a million. For each one, we have a comparable derivative price. So we have millions of derivative price. Then we can simply average out those derivative price, and it is future derivative price. And then we can discount it back with risk-free rate. Then we have present value of derivative price. So we are done. So we can estimate derivative price depending on this interest rate. That is how we use Hall-White model in order to price a derivative depending on interest rate.